Sara Pellegrini and Milan Savić are going to hold the next talk, and they're going to tell us why distributed systems are supposedly very much fun. Let's learn why.
Let me try to get away from it. All right, we can start? Yes. Hi, everyone. My name is Milan Savić.
And my name is Sara Pellegrini.
And we gathered here today to share some unpleasant truths about distributed systems with you.
Yeah. Indeed, once upon a time, there was the monolith. And even with its limitation, it also had some good side, right? It was easy to deploy, easy to debug, everything in a single component. But during time, the needs of the modern application became more and more demanding in terms of flexibility, in terms of high availability, in terms of scalability, and not always the monolith was able to keep up with these needs. So fortunately, we found a solution for everything.
And of course, since the year is now 2022, the solution to any problem in life and also in software are microservices. As you can see, our distributed islands here. Joking aside, microservices stand for some good principles, so you can separate your system into several services, you can scale them differently, you can deploy them differently, write them in different languages, etc., etc. However, in order to make any meaningful business transaction, those services need to communicate somehow. As we can see on our islands, we need a boat to send messages. Looks pretty simple on the surface, but there are some things under the surface.
Yeah, when you look under the surface, the problem begins. Indeed, when you need to deal with distributed system, a lot of things can go wrong, especially when you try to distribute messages among microservices. The network is unreliable, other microservices could be temporary, unavailable, a lot of different problems that were not there when we were dealing with the monolith. So we need to introduce this additional complexity in our systems. And the first question is it really worth it?
And the answer is, it depends. But before answering that question, we must remember the very, very first rule of distributed systems. Does anyone know? Yeah, don't distribute your system. We all know that's correct. However, in certain cases, we can just not go about it. We need to distribute our system. And Sara and I prepared several challenges and several solutions to those challenges. We divided them in two topics. One topic is related to message dispatching, while the other one is related to data storage. We couldn't extract all possible challenges and solutions, but the ones that we find most interesting to present today. So let's start.
Yeah, the first problem you need to deal with when you are distributing your system is message dispatching. We need to improve our business solution in order to be resilient and tolerate the challenges of distributed systems. So in order to understand better the solution we want to propose today, we would like to introduce a sample use case that will accompany us during all the presentation. We have an e-commerce that is implemented through a system of distributed microservices. Each microservice has its own responsibility. And when a user wants to buy something, a command is sent, confirm order command is sent to the component that is responsible for ending this type of command. And if the order can be confirmed, this component will publish an event. An order confirmed event to all the other components that are interested in this event. So as a consequence, they will react in different way. They can send, for example, a mail to the customer or update some projections. So after that, the shipment department want to read the order that are ready to be shipped. And in this moment, the system send a query. So as we all know, there are three main category of messages when we are dealing with message-driven systems.
And that is correct. We know that all happy messages look the same, but not all messages are the same. There are three types of messages that we identified, and Sara showed in the example. The first ones are commands. They are routed to a single component. Usually, aggregate is the one handling it. we usually do not expect any response other than, okay, the system got your command, it's fine. And they basically represent an intent to change something within your system. The second type of messages that we have usually in our systems are events. They are routed to all interested components. We just do not care whether they are handled or not. Event handlers are the one to keep track of handling them. And they represent a fact that something really important has happened in our system. The third type of messages that we have are queries. They may be routed to a single component, or maybe if you want to scatter our query across the system and then gather information back, provide some meaningful result, it can be routed to several components. Those type of messages represent an inquiry to get the state of the system right now. And here we are really interested in the response, right? So not every message is an event, as some people may think. Now we just need to use these messages in our system and to communicate. But if you are in distributed systems, a lot of things can go wrong. And the very first one is?
Message not deliver. This is the first common problem that you will face when you distribute your system. And this can happen for several reasons, because, for example, the message doesn't reach its destination, or because the message reached the destination, but it is handled, but the confirmation cannot come back to the initial component. So the reason could be different. And let's see now how we can tackle this problem. So let's say that our friends want to buy something on our e-commerce, and when you click on the buy button, what happened? A request payment command is produced and sent to the component that is responsible to perform the payment. And normally what happens is that the message reaches its destination, it is executed, and the confirmation is sent back to the initial component. But in less fortunate case, it is possible that the initial component does not receive any confirmation back. So whatever the reason is, the initial message didn't reach the destination, or the confirmation couldn't come back. A first possible solution to tackle this problem is to implement a retry mechanism. So if the first component does not receive any confirmation back, or if it receives an explicit error, the infrastructure component should retry, sending multiple times the same command. This is a first purely technical solution. We identified the technical solution with this symbol, with which we can try to tackle this problem of message not delivered. Let's see now another solution.
So another, oops, sorry, not back, forward. Another solution is a circuit breaker, and I got the privilege to talk about it because Sara does not like this solution that much. The use case is pretty much similar. We have a user, he or she wants to buy something in our event store, and now we need to request a payment. We send this request, but the payment provider is not available. What we can do in this case is just to break the circuit and say, okay, no further requesting from this payment provider makes sense, so we're just going to make a shortcut. We are going to say when following requests arrive, we are just going to answer right away, okay, this payment provider is not available. However, we have to be really careful not to keep this setting forever. We need to, from time to time, check whether the payment provider is available and then actually send the message. With this, we are going to improve performances a bit. And this is another technical solution that we are adding to our toolbox. There are more.
Yeah, the reason why I don't like circuit breaker is because by evolving a little further, the same concept, we can achieve more. We can achieve a failover mechanism. So in this case, whenever a component is unable to perform its duty because it's temporarily unavailable, what we can do is to forward all the requests that was initially addressed to that component to a second instance. This second instance can be already available as a replica of the first one, or can be instantiated on the fly to meet the temporary needs. And in this way, we do not have any problem. So this is another technical solution for the same problem. Let's see now how we can handle this problem from a design point of view.
When it comes to design, we can add deadlines. So there is a request for payment. Before sending this request, we are going to set a deadline. We are going to set how much time we are comfortable with waiting for this request to be sent and a response to arrive. We're going to send a request, and our payment provider is not playing well again, and the deadline will occur. In order to handle this deadline, we are going to need to compensate somehow. This is an order, it needs to be paid, so the best thing for us now is just to cancel the order. With this, we are going to basically compensate and solve this issue. And we are going to use this specific symbol to depict all design solutions in our toolbox of solutions.
So message delivered multiple times. This is another problem that is very common. And bear in mind that this problem can also be introduced by the retry mechanism, for example, that we introduced before. Because in general, when you are in a distributed system, if a component is sending a message to another component, doesn't receive any confirmation, it is impossible to understand exactly which is the reason. So if the message never arrived at the destination of, if it was already delivered and handled, but the confirmation was not delivered back to the initial component. So for that reason, the only way we have is to build our application in such a way they can tolerate multiple sending of the same command, of the same message. So the first technique, the first solution that we are presenting is to make your messages idempotent. What does idempotence mean? Idempotence is a property of a function such that no matter how many times you invoke it, you obtain exactly the same result. So let's see an example in our e-commerce system. So someone wants to buy a banana, but after some time it changes its mind and decides to buy 2 bananas. So what he does is to increase the number of bananas in the car. If we decide to use an increment item number command, the first time this command is executed, the number of bananas goes from 1 to 2. But what happens if by mistake this command is delivered twice? So in this case, the number of bananas goes from 2 to 3. This is not what we want. And the reason is because increment item number is not executed in an idempotent way. So how we can solve the same problem using idempotent command? So what we can do is to change a little bit the semantic of the command and using an update item number command. In this way, the first time it is executed, the number of banana goes from 1 to 2. But if by mistake it is executed a second time, the consequences are not important because the number of banana goes from 2 to 2 again. So this is an example of an idempotent message. So the message is executed in an idempotent way. So this is an extremely powerful tool in distributed environments. This is a design solution. And designing your messages to make their execution idempotent is the key to make your application really resilient.
But we can do more. So this is a case where we have a unique identity. And it is really important to have this unique identity for this one to work. We have confirm order command. We are going to load up the aggregate with all its events. We are going to handle it. We are going to update the state of the aggregate, and we are going to publish an event that this order has been confirmed. If for some reason we receive the order again, confirm order again command, we are just going to check the state, and we are going to see that the state is updated to be confirmed, and we can just say, okay, we can put this message on the side, we are not going to handle it again. We are not going to publish an event again because it just makes no sense and it could lead to some inconsistency in the system. So this is a solution that we call compare swap. This is something that you probably know from programming languages, Java, C#. They all have the concept of CAS. While there it is a technical solution, we denoted it here as a design solution because it really depends on your domain how you're going to implement it. You cannot provide it as an out-of-the-box solution that can be just used. But now let's see what we can do when there is no identity. This is a case where we have a warehouse. It stores some goods, bananas in this case, and we want to deliver 2 of them to our customers. For this case, it's really important to know that there is no way for us to uniquely identify bananas in the warehouse. We receive remove items command, we are going to handle it, event is fired, we update the state of the aggregate, it is now 14. For some reason, we receive the command again. There is a network glitch or something like that. There is no way that we can use idempotency or any other technique previously, so we are just going to wrongly handle it again, publish an event, and update incorrectly the state to 12. So, Sara, what can we do here?
Yeah, as you mentioned, it is impossible now to use identity because there is no semantic identity in this use case. So the only thing we can do is to introduce an artificial identity. For example, we can use the unique identifier of the command itself. When the first time this command arrives and it is executed, we save this identifier in a cache, a temporary cache, and if the same command is delivered a second time, we know that this has been already executed, and we just drop it. We don't execute it twice. So this is a technique that is called the duplication, and it is a technique. It is the only technical solution that we propose here, and this should be used only when you cannot use one of the other 2 solutions we propose. Basically, when you have no identity, so you cannot implement a design solution for that. So let's now move to another topic, another problem.
And that challenge is what happens if messages are delivered in the wrong order. Reasons for that could be various. So maybe you're not using the right protocol for it. UDP does not have a guarantee of order. You want to use UDP for the speed. Or maybe the structure of your system is done in a way that you cannot have an order guarantee. Maybe you have several TCP channels opened between 2 services communicating with each other, and there is just no way that you can impose order guarantee on several of those channels, right? So we need to do something more. The very first thing that we are going to explore here is, again, really the same use case. So we want to confirm the order and we want to request the payment. Order is confirmed, we request the payment, payment is confirmed, and this is really, really happy scenario for us. But now let's say that due to some network partition or weird network configuration, those messages are not received and handled in the expected order. So we send them in the correct order, but they are received in different order. If they are both handled successfully, it is still okay, right? But what happens if the order has not been handled successfully? For us, being an online shop, this is a really good situation because we received the money, but we didn't deliver any goods. But if we want to be more ethical and want to protect our user, let's say that we want to solve this issue. One of the things that we can do is basically just chain our messages. So we have confirm order, request payment. Firstly, we are going to send confirm order, wait for it to be confirmed, and wait for a reply back. Then we are going to send request payment, and once it is confirmed, then our use case is completed successfully. So this is the first solution, and you can guess that it is a design solution.
There is another solution that is very, very similar to the one that Milan explained, but is implemented in a different way. It is to create an order to enforce the order using a cause and effect mechanism. So in the same example as before, when the confirm order command is sent, it is handled and executed, and an order confirmed event is produced. So is exactly the order confirmed event handler that trigger the sending of the second command. So the request payment is sent as a consequence of the order confirmed event. In this way, it is impossible, of course, that the payment request is sent before, because it is exactly the confirmation event of the order that triggers the sending of the next command. So this is another design solution that we have for this problem. Then we have we want to propose a solution that you can use only in very particular situations.
And that is leniency. In this situation, we have, for example, temperature sensor. It sends temperature readings to a cloud service. It is collecting it, and let's say that in this cloud service, we want to have a logic, for example, to turn on heating or to turn off heating. If it is done in a naively way, let's say if the threshold is 21 degrees Celsius, and we say that if it passes after 21, we want to turn on cooling, or whatever. It doesn't make much sense. But if you receive messages in different order, we can end up in the wrong state, right? We can turn off cooling while we wanted to turn it on. In order to improve on this, what we can do is to introduce a time window in which we are going to collect all those temperature readings. We are going to impose a reduction function on those values that we received. Here, for example, we are using an average, or you can use a mean, whatever, and then reason about the reduced value. With this approach, hopefully, we are going to minimize the surface area for which error can occur. So this is, again, a design solution, because it really depends on your domain, which reduction function you're going to use, how you're going to reason about those values. Now, let's see what we can do from technical perspective.
Yeah, as Milan introduced before, why don't use a protocol that can enforce itself, right? A transport protocol that can guarantee the ordering. And indeed, in a certain case, we can do that. For example, in this example, we can guarantee the order of messages coming from the orange component to the blue one if you use a TCP channel. That's great, but what happens if we need to scale up the blue component? So in this case, we cannot guarantee the order of messages, because there are two TCP channels and the two blue components are operating concurrently. So it is impossible to guarantee the order of execution of these messages. What we can do is to decide the dispatching of the messages accordingly to the sequentiality. So we can decide to dispatch all the messages that need to be executed sequentially to the same component. In this way, the TCP channel will guarantee the ordering. So for example, we can do that using an hashing algorithm, a consistent hashing algorithm, and using as a key the key that represents the sequentiality. In our e-commerce example, for example, we can say all the commands that are, all the messages that are related to even customer code will be dispatched to the first component, to the first instance. All the messages with the odd customer code will be dispatched to the second instance, because for us it's important that messages for the same customer code are executed sequentially. We don't care about concurrency across customers. So this is great, but what if instead of scaling up the blue component, we decide to split it in two different components, a black one and a green one? They can handle different type of messages. So what happens if we need to enforce sequentiality between two messages that must necessarily be delivered to different components? In this case, we cannot use this technique, and there are no technical solution that can solve completely the problem of message delivered in the wrong order. So the transport protocol, together with the consistent hashing, it's a technique that can improve can mitigate the the problem of message delivery in wrong order, but this solution must always be implemented together with the other design solution that we proposed before. Let's see now what happens when non-functional requirements changes.
Or we were told that not to use non-functional requirements because then your system does not function. So we use infrastructural requirements. So for a certain reason, we want to deal with this red component. We want to build it in a different language. We have a new team that is going to be responsible for it, or we want to deploy it using different technology stack, whatever. Or maybe we just want to scale it out differently. Maybe this is our ordering component. We have our orders getting high, so we want to have more instances. So why scaling the whole system when we can scale out only the order component of our system? So technically, things are changing, but when it comes to business perspective, all the code is the same, right? There are no any business requirements to be changed, and we want really to lock that. We don't want to change any business code. We want to change only infrastructural components. And there are one really important principle that is going to help us in this situation, and it is called location transparency.
Yeah, location transparency is a very important technique that says that a component should never be aware of the location of the other components it interacts with. Even more, the component should not even be aware of the existence of any other component. So what it can do? So a component, can express its needs to the rest of the world sending commands. And can also express affect, for example, something that happened, sending events. But is not aware of who is interested in these commands, events, and query. So let's see how it is in practice.
Yeah, let's try to put location transparency in practice. Here we have two components, and they want to communicate with each other. One way of doing so is sending a request and a reply. So a purple component sends a message directly to a blue component. And we can say that this is not so location transparent, right? In order to overcome this issue, we are going to introduce an infrastructural component. We are going to call it a message bus, because it delivers messages. So now when a purple component wants to send something to a blue component, it will use this message bus. What this message bus also gives us is boundaries within our system, right? So now we can say, me as a purple component really do not need to know anything about other components. The only thing that they need to know is the API of other components, which in our case are messages. I need to know commands that the blue component is able to handle, events and queries. So what we are going to do is just to use a message bus to send messages from one component to the other. If we are in the same deploy unit, this is going to be a local implementation of the bus. If we want now to separate our components into several services, then we just change the implementation of the bus from local to distributed one.
Yeah. And this is very powerful because it allows us to change the implementation of our infrastructure without changing a single line of business code. So at the very beginning, when we start a project, it makes a lot of sense to not distribute your system. You don't want to deal with this complexity. You have a single, well-structured monolith. And in this phase, the components that are inside this monolith can communicate with each other using a message bus, an implementation of a message bus that is able to deliver messages inside the same executable. But if we need, for example, because we want to scale up, to move the right component outside the monolith, in this moment, the implementation we use for the message bus is not suitable anymore because it is not able to deliver messages outside of the monolith. So we can do it simply to change the implementation of the message bus using an implementation that is able to deliver message in a distributed environment. So location transparency starts with the definition of a good API that is able to decouple in a very strict way the business logic from the infrastructure logic. And in this way, we can evolve the implementation depending on the needs that can arise during time. So, last but not least.
Yes, it is performance, right? This is something that we worry only when we deploy to production. Somehow, Sara and I put this as the last topic. I don't know why. Maybe because we are engineers. I don't know. But I mean, there could be various reasons for having a bad performance, right? Maybe just there is a network partition this specific point in time, and our system cannot take that load. Or maybe just the load was not expected for that period of day. I don't know. Or the system that is the component in the system that is processing those requests is just slow by its nature. It cannot be faster anyhow. Anyway, we need to deal somehow with it. The very first thing that comes to mind is just to introduce streaming, right? Instead of using request reply that we used to use, right? We are going to introduce stream of messages. Rationale behind this is pretty simple, right? Instead of having an overhead for each message, opening connection for each message, we are just going to open two connections, long-lasting connections that are going to be used for streaming messages. Now we need to have a correlation between request response, but that's not such a big deal. So streaming is a solution that will help us here. It is a design solution, and there is a really good question why it is a design solution. Because you may say, yeah, HTTP2 supports streaming, HTTP1 does not support streaming. It is there, right? It's on the protocol level. I just do not care. However, when you're building your components, when you're using your messages as the API, it's really important to know how to send those messages. If you say that these messages should be sent in a request reply manner, then your API is dependent on it. Regardless of your underlying protocol, this will have an effect, right? So if you start providing your API in a streaming fashion, then regardless of the protocol underneath, components are going to use it in such a manner. If later on you decide to switch the protocol, you can still keep the API and you do not need to change anything else. So any other component can use the same API to communicate with it.
Yeah, but not all that glitter is gold. And of course, streaming your messages will improve the performance of your system as a whole. But on the other side, you need to be very sure that all the components in the pipeline are able to keep up with the pace of the messages. If this doesn't happen, the consequences are pretty obvious. And we call these families of problem with the name of impedance mismatch. So one solution we can adopt to tackle this problem is to use back pressure. So if a certain component, maybe not the fastest one, it needs to handle a higher load than expected, what happens? The component can buffer these messages before to handle them for a certain period of time, but if it remains active for too long, the component will collapse at the end. So in order to avoid it, we can use a back pressure mechanism. It's not the first component that push, but it's the second component that pulls. This is a great solution when you need to stream your message, but remember that this is not always applicable, because there are situations where it is better to fail than to slow down. Think, for example, that the stock exchange market, this is not a good idea to slow down in certain cases. Let's see now the last solution.
And the last solution is batching here. So it is just an improvement on the streaming. I believe we all know what batching stands for. Nevertheless, I'm just going to quickly go over it. So rationale here is, again, instead of sending a single message, having an overhead for headers, for metadata, we are going to group those messages in a batch, and then we are going to send that batch of messages away. And with this, we ended all challenges and all solutions to those challenges when it comes to the message delivery umbrella of problems that we have in distributed systems. Now we are going to move to the data storage issues. Data storage is usually something that we take for granted, and I know Sara and I do not take it for granted because we are building a data storage. So we wanted to share our pain with you, so you know it as well. The very first, so we are going to present only technical solutions because we don't want to bother you with design solutions. So you don't, at least it is important for you to choose the right type of the storage. For example, if you're using event sourcing, you should use an event store. The very first issue that we are going to examine here is data availability, right? So today, data is really important, and we want it to be available all the time. So what can we do here?
Yeah, when the data are stored in a single instance, of course, we have a problem. We have a single point of failure. So if this single point of failure is not available, this instance is not available, the data are not available either. So what we can do, the solution here is to replicate data across multiple instances. But unfortunately, replicating data in a distributed environment, guarantee the consistencies of all of them is not a trivial operation. Lucky for us, there are some protocols that can help us.
And those protocols are called distributed consensus protocols. Now we're just going to, on a high level, see how they all work, basically. We have a bunch of clients. We have a cluster of servers. Let's say that these servers are basically data storage servers, and a client wants to store a data. It will send a request to one of the servers. Usually those are protocols that expose the leader. So you send a request to the leader of the cluster. So the leader is going to record this information in its transaction log, and it is going to replicate it to other instances. To other transaction logs of other servers. Once the majority of nodes, or certain number of nodes, depending on the protocol, confirms that this information is okay to be durably stored, we consider this point in time a commit point. And from that point in time, until while the cluster is available, that information is going to be available for us. Once we have a commit point, then we are going to apply this request to the state machine. Basically, we are just going to durably store it because we are storage, and then we are just going to send information back to client. Okay, your data has been accepted and durably stored. Having in mind that transaction log is the same on all servers in the cluster, the state machine is deterministic and implemented in the same way. Basically, we derive to a conclusion that all servers are going to have the same data. Hence, our data is replicated. We chose one specific protocol here.
Yeah, we chose Raft for implementing our project because Raft is very understandable. So it's famous for its understandability. It is a protocol that is based on absolute majority of nodes. So you need the absolute majority of nodes in order to have the cluster available. So if you have 3 nodes, you need to have 2 available to have the cluster. You can tolerate the failure of 1. So when we talk about data availability, the only blade we have in our knife is replication, because the only solution is to replicate the data. So, and again, last for this category, of course, performance.
Yes. Again, the very last thing that we worry about is performance. So the very first thing that we can do is to layer our storage. We are going to have a primary and secondary layer. Primary layer is put on fast disks, while the secondary layer is put on disks that are not that fast but are cheaper, right? So when we replicate our data, we send it to the primary layer. Primary layer forwards the request to the secondary layer. But now, having in mind that the primary layer does not have that much space, at a certain point of time, it will just start deleting old data, right? And it will continue replicating information to the secondary layer. The idea behind this is the less data it needs to handle is going to be faster. And we are usually going to need the most recent data. in cases where we do not need the most recent data, we still have it available in the secondary layer, but that will come with performance penalty. Yeah. So this is layering storage, and it will help us with performance.
Horizontal scalability. So if, as we said, we have multiple instances that contains a replica of the same data, in this case, you can take advantage of this instance in order to parallelize the reading operation and in order so to speed up your system. And unfortunately, if you are using, for example, like us, Raft protocol, this doesn't work for writing operation. Because in Raft, all the writing operation must pass through the leader and they must be acknowledged by the majority of the node in the cluster. So this operation cannot take a real advantage from an increased number of nodes in the cluster. But a read operation, yes. So this is another strategy that we can use to improve performances if you are doing a lot of read operation. Let's see now the last solution.
Last solution is sharding. The idea is somewhat simple. So each node in our cluster has a sharding key. It's a value assigned to it. And each node knows how to calculate the sharding key based on the incoming data. If those two values match, then I'm going to store it on my machine. If they do not match, I'm going to forward it to a machine that can store it. Consequently, if I need to deal with less data, I'm going to be more performant. And with this, I believe that we ended. So this is the very last thing. But there are some things that we would like you to go away from this talk.
Yeah, so we presented the most common problem that we found when you start distributing your system. We have seen many of distributed systems, and these are the most common problems. And we presented also some solutions, some common solutions. But there is a common denominator, a general rule that we think is important, that is the message that we would like you to take away.
So we've seen two types of solutions to problems in distributed systems. Ones are technical solutions, while the others one are design solutions. We as developers usually try to seek for a technical solution always, right? It's easier, it's our comfort zone, we don't want to get out of it, I can put my headphones and just code it out, right? But it's not always the best solution. Sometimes it is much better to talk to business to see whether we can adjust our design, whether we can adjust our business process somehow that implementation is more maintainable, more durable, etc., etc. And there are also another thing that we want you to go away with.
To be reactive. So we know that be reactive is a way of life, but today we want just to focus on the first three reactive principles. So first of all, stay responsive and embrace this asynchronous approach, not only dealing with handling the expected scenario, but mostly detecting and dealing with the errors.
The other principle is to accept uncertainty. It is really easy to communicate between components once you're in single deployable. Everything is in the same process. There is no way that message delivery can fail, that you can have messages delivered several times, etc. All the challenges that we've seen. There are some solutions out there, technical solutions that you can use to abstract away the network, right? It is right here, right? This is not a good idea because if you design your system in such a manner, it is not going to behave well and you're going to have a lot of things just put under the carpet. So have in mind that your system is going to be distributed, use messaging between components and use right abstractions on top of it.
And finally, embrace failure. So as Milan just pointed out, failure is just one of the possible situations. It's not an exceptional situation. It's just one of the many scenarios that we need to handle. So the failure must be explicitly represented and handled in your code base. So that is the last point. Thank you for attending.
And yeah, this is
the last slide.
Yeah, if Twitter is still active, these are our handles. Yeah.